Okay, Michael, I think you're good to go.
Alrighty. Thank you, Ken. So my name is Michael Smitasin. I'm a cybersecurity engineer here at Lawrence Berkeley National Laboratory, and I'm going to be talking about network tapping for Zeek. So it does say it's a deep dive, but I'm going to actually give some kind of groundwork level stuff as well to kind of help out those who don't work on a regular basis with tapping and tap aggregation. So some groundwork definitions. I'm going to be talking about taps, tap ag, and Zeek. Taps, largely you can think of it as a way of getting copies of traffic out of your network. Tap aggregation, like it sounds, is aggregating and manipulating that copy of traffic. And then Zeek is an intrusion detection system, but it's actually more than that. It's a framework for kind of working with traffic and distilling down information, so you're not just looking at raw packet captures. And then because it is a framework, you can write policy and have it take actions on traffic and alerts. So the formula is we've got links between network devices. We can install taps on those links, get copies of traffic out of those taps, put it into TapAg, do manipulation on that traffic, and then send it off to a tool like Zeek or a Zeek cluster if you're load balancing across multiple nodes. Quick outline. So going to be talking about taps, tap aggregation. We'll look at LBL's environment, how we have taps and tap aggregation deployed. Talk about scaling up with load balancing, look at traffic filtering, both static and dynamic. Talk about TCAM limitations, some ingress, egress, ACL workarounds to those TCAM limitations. Look at identity VLANs, and then wrap things up with tapping cloud email, visibility in the cloud, and then tapping and tap aggregation at 400 gigabits per second. So before I get into taps, I did want to mention some technologies that are very similar to taps and serve a very similar role. And they go by many names, so mirror ports, monitor ports, span ports, but it's basically on-device packet replication. So on your switch or router, you're configuring something that is mirroring traffic from one interface to another interface. And that has some positives and negatives. So because it's just on the device, it's typically free. A lot of these devices just come with that functionality, and it's just a matter of configuring it. You can also apply filters on the device itself. So before you even output the copy of traffic, it's been filtered down to specifically what you want. If you want to only send DNS traffic or HTTP traffic, you can configure a filter. The cool thing is it's generally non-disruptive to add, change, or remove it because it is a configuration item. And so you don't have to worry about taking down a production link to start doing this. There are some technologies that allow encapsulation of that mirror traffic into like UDP packets, and then you can just send it over a typical IP network. So RSPAN and lawful intercept are examples of that. Some negatives, though, is because it's in-band, you may run into resource contention. If your packet or if your router or switch is getting really hammered and it can't keep up with packet replication, you may not have that visibility into what's going on kind of at the crucial time when you need it. You might also run into hardware limits. So I've seen devices that you can only configure 2 span ports per device or per line card. And then also you might have oversubscription issues where if you're tapping a 1 gig, or not tapping, but you're mirroring a 1 gig interface, that's 1 gigabit per second transmit and receive. And so you got to send that out another interface. And if that interface is also only 1 gig, you're potentially oversubscribing it by 2 gigabits per second and causing packet loss in an unpredictable way. So that's where taps come in, because taps are a completely out of band, separate physical device that you're installing on a link between 2 devices. And they can be completely passive and unpowered. So if you're installing in a location where it doesn't have electricity, or you don't want the loss of power to cause your production link to go down, passive tap is great for that. If you're dealing with fiber taps, they can be all light, and so you're not having to worry about the oversubscription problem. You do get 2 pieces of fiber that you have to plug into a tool or into your tap ag, but at least you're not worried about kind of unpredictable packet loss from oversubscription. And then in our experience, the passive optical taps have been super reliable. I can't even really think of a case where we had one fail that was already in production. I think the few issues we've had, it's been like we go to install a new one and it doesn't work. Maybe it was damaged in manufacturing or transfer or something like that. The price could be either a positive or negative depending on how you look at it. So the upfront cost of taps, are hundreds of dollars, maybe up to $1,000 per device. So per tapped link, which could be kind of high, but if you're comparing it to doing a mirror port on a big expensive, edge router that you're paying potentially $100,000 per line card or something, and then it's tens of thousands of dollars per interface, it may be cheaper to install tap rather than eating up a production interface on your big expensive router just for port mirroring. And then one of the hard things to get around is that because it is a separate physical device that you're installing on a link, it is going to be disruptive. Although what we have taken to doing is installing taps with a link as it is provisioned by the networking group, so that even if we don't have any immediate need to go and plug in the output from that tap, we at least have the tap installed somewhere, and as we get that need, we can just go and plug in the outputs. So taps come in different flavors. There are copper taps. If you're tapping like Cat5e, Cat6a, there's optical taps. They've got active ones and passive ones. The active ones are good for signal regeneration if you're concerned about light budget, and I'll talk about light budget in a second here. And then there are also things called fiber patch tap cables, which basically are the same functionality as a passive optical tap module, just in the form factor of a cable. Not super useful for security purposes, maybe, but I hear they're pretty popular in high frequency trading. Quick detour to fiber, just for folks who don't work with fiber a whole lot. When it comes to installing taps, you do need to make sure you understand the connector types and the fiber types. The common ones you'll run into for connectors are LC and MPO, with MPO typically being the shorter distance, higher speed connector types for, they have multiple strands of fiber per connector. So 8, 10, 12, 24, I think, strands of fiber per, strands of fiber per cable. And so you're doing like 40 gig, 100 gig speeds, but within the same room or within the same building. And then the types of fiber, single mode and optical, or in multi-mode, stands for optical single mode. OS2 or OM4 is optical multi-mode. You can go super deep with fiber. So just as an example, there are different shapes to the fiber ferrules, UPC and APC, and you don't want to mix those because you can actually end up damaging the connectors if they even seat at all. So I mentioned light budget. Light budget is basically, so when you're transmitting light over a distance, you're going to lose light both because of the propagation of light and any of the connection points along it. So patch panels, for example. And there is a threshold on the receiving end for which the receiver can actually bring up that link. If you dip below that threshold, then your link will come up. And so that's important to consider when you're installing a passive optical tap, because they are sold in split ratios, like 50-50, 70-30, 80-20. That refers to the amount of light that they pass through to that kind of production receiver and the amount that they split off for your tap ag or your tools. And so if you're doing this calculation and you find that even without having a tap installed, you're up near that threshold, if you were to go and install a tap, you might dip below it and then your production link doesn't actually come up. And so in that case, you could do an active optical tap, for example. And where this gets interesting as well is if you need to install multiple taps on a single link. So for example, we do this where we have redundant locations for our tap aggregation infrastructure. And we want to have them be completely redundant to each other so that if one goes offline due to a power outage, the other is still up. And so we want to have passive optical taps in line. But the risk there is that they may cut down on your light so much that your production link doesn't actually come up. So one option, instead of just doing 2 taps in line here, is you could install just 1 tap in line and then split the output to your tap aggregation. And in fact, you could do an active optical tap here, but still use a passive optical tap here, so that if your power is lost in this location, it doesn't take down your production link. And you can actually check the light levels on the devices. So you can just log in to them and issue a command. And I threw up some example commands there of some typical platforms. And basically, it'll show you your threshold and your power levels. So you can check that before you go and install a tap and see, okay, I've got enough budget to do, a 50-50 or 70-30. And it might help inform that decision about what split ratio you use. So if you decide you do want to install taps, there's the question of where in your network do you install them. And when I think about a hierarchical network architecture, there are several places that you can install taps. I typically think of it as the further you go down in that hierarchy, the closer you get to your clients, the more number of links you have, and that you would have to tap to get complete visibility there. And so at the top, tapping between the internet and your border routers, typically people have a small number of links to the internet, unless you're like a service provider. And so a few number of links that you have to tap. That gets you visibility between the internet and your network, but it also gets you lots of scanning noise because it's beyond any blocking capabilities that you have for border routers or firewalls. So then you can also tap between your border routers and your core routers, which would get you the same kind of visibility between your network and the outside world, probably a small number of connections as well, but it's behind your border blocking. So you may no longer have to see all of that scanning noise. And then you can tap between your core routers, your internal routers, between your internal routers, your access switches, and your access switches, and your clients, although then it's starting to get really impractical and cost prohibitive if you have 10,000 clients going and tapping each and every one of them. Although you could do it in a strategic way where, say, you have a very important finance system or HR system that has PII on it, you could choose to just tap that one server as opposed to like tapping every single one of your clients. So the way LBL does it today is we tap between our border routers and the internet, and we call that our external DMZ taps. And we tap between our border routers and our internal routers, and we call that our internal DMZ taps. And again, the difference there is that the internal DMZ is behind our border blocking, and so it excludes all that scanning noise that's already getting dropped because it's blocked at our border. And then the last place we tap is between kind of a select number of access spine switches in our internal routers. And this gets us good visibility between certain subnets because the traffic has to go up to the subnet gateway on the internal router before it gets routed to any other network. And so we get that visibility there. And that's because we're not actually tapping the hundreds of different leaf switches or access leaf switches throughout our campus. It just cuts down the number of taps that we have to install. In the future, we are planning to add core routers, and the plan is that we will no longer tap between kind of the core routers or border routers and our internal routers, but instead we're just going to install many more of these spine switches and tap between those internal routers and the spine switches. And that will actually let us condense the functionality of the internal DMZ taps and our intranet taps kind of into a single layer of taps. And where we feed those will kind of make sense in a second here after I talk about tap aggregation. So now you've got taps installed, and you have to send those taps to something. You could just go and plug it into tools like Zeek, but that doesn't scale real well. You start getting into tens, potentially hundreds of tapped links, and it may make sense to then aggregate that traffic into a single place and send it to a single tool or a single cluster of tools. So you can do this with things called tap aggregation switches. also known as network packet brokers. And you can kind of think of them as layer 2-ish switches that do some functionality to manipulate traffic. So this is, copies of traffic coming out of the taps. You can aggregate that tap into a traffic stream, or those taps into a traffic stream. You can then apply filters to it if there's traffic you don't want, or if there's specific traffic you do want and you don't want the rest. You can replicate the traffic streams across multiple tools if you have, Zeek and Suricata and FireEye, whatever. And if you need more capacity than a single tool can provide, you can also distribute or load balance it across multiple tools in a cluster. And so this is all functionality that you can largely do in a single, 1U TAP-AG device today. But when we first started working with the Arista tap aggregation switches, we couldn't do both 100 gig tap aggregation and the more advanced features like egress filtering and symmetric hashing or load balancing across a cluster of nodes. We couldn't do all of that in one switch, so we had to have kind of two different switches. We had the 100 gig tap ag, and we had a 10 gig output switch for all those advanced features. And even though you can now do this in a single switch, we've kind of preserved that design because it gives us more flexibility. We can send a completely unfiltered, unadulterated stream of traffic to tools that can accept it. We can also have multiple output switches if we want to test out different models of switches or different configuration on the switches, or just have redundancy if we want to be able to patch this switch and not take out all of our tools and have all the shields down. So I talked about where we tap today, the external DMZ, internal DMZ, and intranet taps. So we feed those to corresponding TAP-AG infrastructure. And our primary one is our external DMZ TAP-AG infrastructure. And we have the two different layers here, an aggregation layer and an output layer. We have a 1 gig, 10 gig switch, and then a 40 gig, 100 gig switch. We basically feed the 1 gig, 10 gig into the 40 gig, 100 gig, and then output that to 10 gig output switches that are doing the filtering and the symmetric hashing. And then we have a very similar environment in a separate location, and that's where we're doing the two passive optical taps on a single link feeding to the two separate buildings, basically just as redundancy in case one of the buildings goes offline for some reason. But we are very space constrained in that second location. So instead of having a 10 gig switch for aggregation, we actually, they're the same exact models. So we just do that same functionality on what would be our output switch. It makes the configuration a little bit less obvious to follow, but considering that we just didn't have the space to install an extra switch, it ended up being what we had to do here, and it's not that bad. Where it does get more interesting is our internal DMZ and our intranet tapping infrastructure. So today, those are two separate layers. They're installed on different types of links, but we feed them into a single TAP-AG infrastructure. So we still have the aggregation layer here and an output layer, but we're feeding both sets of taps into it. And then we basically identify those input interfaces as being for internal DMZ or intranet tools. And then we apply filters to them. And you can kind of see here, the orange goes to our internal DMZ and the blue goes to our intranet tools. And so then as we transition to the future plan of just having a single layer of taps for both internal DMZ and intra, those will all just continue to go to the same TAP-AG infrastructure. So I alluded to, we use Arista tap aggregation switches. So we've been big fans of that. It's pretty easy to use, and the pricing is pretty decent for what you get. We use basically a single model line now, the 7280 model line, and then within that line, they've got different models. Largely, we use a dense 1 gig, 10 gig, and future 25 gig switch, and then a denser, fast, higher speed switch that does 40 gig, 100 gig today, and we'll do 100 gig, 400 gig in the future. Worth pointing out that the Arista switches do require a special license to do tap aggregation. I think it either was or currently is called Z mode license or Z licenses. And then for our NICs, we're using Miracom 10 gig and Intel 10 gig. You do have to purchase a sniffer license for the Miracom as well. So I mentioned we like the Arista because the configuration is very easy. So I figured I'd just show a simple example of what the Arista tap ag config looks like. Basically, you just have to put it into aggregation mode and then configure the interfaces as input or output. And that's by this switch port mode tap or switch port mode tool configuration line. And then you put them in a group, and that group basically maps the input to the output interfaces. And so that works, that super simple configuration works pretty well for up to about a gigabit per second analysis for Zeek. And that is bound by the CPU core speed because you basically have one Zeek worker process running per core. And they can do, about 500 megabits per second to a gigabit per second of analysis. If you want to go faster, if you want to analyze more than that, what you can do is load balance across multiple Zeek worker processes running on multiple cores within a single server. And you can do that using the NIC, the Miracom NIC or the Intel NIC with the AF packet. And then above that, if you were talking about, 25, 40, 100 gigabits per second of traffic, you could try to do that in a single server with lots of cores and a high-speed NIC, but it may actually be easier to just have multiple servers running smaller number of cores each. And then you can do load balancing at the tap aggregation level with a link aggregation group or port channel. And I'll show the config for that in a second, but this is the configuration for load balancing across multiple Zeek worker processes using the NIC. So with a Miracom sniffer driver or with AF packet on the Intel NIC, basically setting the number of processes and pinning CPUs to it. But so then if you want to do 5 or 10 Zeek nodes in a Zeek cluster and you want to load balance across them, the important thing to do is to ensure that all the packets for a given connection are sent to the same Zeek node so that it can reassemble that connection properly. And they're not just getting sprayed across all your different interfaces and all your different Zeek nodes. So you can do that with something called symmetric hashing. In Arista, that involves basically configuring a load balance profile where you specify the criteria that you want the switch to use when it selects which interface to send a packet down. So in our example, we're using IPs and port numbers. We have them set to symmetric mode. And then we are excluding things like MAC addresses and MPLS labels from that hash calculation. And then we apply that load balance profile to port channels. And so then when we create a link aggregation group for our Zeek cluster, we put it in a port channel and it inherits that load balance profile. So one of the other cool things you can do with link aggregation is you can do traffic filtering. A reason why you might want to do this is if you have like a malware analysis tool that can only do 3 to 5 gigabits per second of traffic analysis, and you've got 30 gigabits per second of traffic that you're actually tapping. You might also do it just if there's traffic that you're not interested in seeing, you're never going to actually do analysis on that traffic, and sending it to your tools would just be eating up bandwidth in your tap aggregation infrastructure. So one of the ways you can do filtering is just ACLs, static ACLs based on IP addresses, prefixes, port numbers, protocols. You can also do what we refer to as control packets, and I'll show an example in a second here. And then you can do packet truncation, where you're just saying, the first X number of bytes in any packet, accept that, and then drop the rest. So control packets, you can think of it as like matching on TCP header flags, for example. So we do this for SYNs, FINs, resets, and fragments. And then we also just accept UDP, GRE, and ICMP traffic. So in an example of a TCP connection here, the yellow packets you would get sent down to your Zeek or your tool. So you'd see SYN, SYNAX, and then FINs. but you're not doing analysis on these tens of gigabytes of payload. And that's very useful for things like scan detection, where the scanners are only ever doing SYNs or SYNACs. And so you only need to really look at those packets, and you don't need to do analysis on payload of even legitimate connections. This is what we do for our scan detection dedicated Zeeks. And you could do something similar with packet truncation. Again, for those, we were just saying the accept up to X number of bytes per packet. If you're only interested in looking at like the IP header, for example, you could truncate it just to the length of an IP header. But the downside there is you are getting all the payload packets as well. And if all of this looks exactly the same from an IP header point of view, that may not be that interesting. You may just be kind of eating up bandwidth. So what we prefer to do is something a little bit more dynamic. So dynamic traffic filtering or dynamic ACLing or shunting. Basically, we accept those same control packets, and then we also accept up to a threshold of connection size. So we're going to accept, let's say up to 128 megabytes of the payload as well, and then we'll drop the rest. And the way we do this is using a Zeek policy. So basically, Zeek is tracking the size of a connection. And in that policy, we've defined the criteria that we want it to use to identify a connection as being, a big flow or an elephant flow, and then trigger shunting on it. So because it's a Zeek policy, you can kind of use any fields that are available in Zeek. You can use connection size in one direction or both directions, packet counts, ports, protocols. You could even use things like country codes. And so it's gonna identify a flow that is a candidate for shunting. It's gonna trigger an action. That action uses a Python script called Dumno that was developed by Justin Azoff when he was at NCSA. And it just interacts with the API on an Arista switch to let Zeek put in a 5-tuple ACL dynamically. So once it triggers that shunt action, it puts in the ACL. The rest of the packets matching that 5-tuple get dropped. And then when it sees the fin or the reset, or I think if the connection times out after a certain period, it'll go and clean up that ACL so that your ACL list doesn't, or your list of ACL entries doesn't grow indefinitely. But one challenge with ACLs is you might run into TCAM limitations, which is something that we ran into on the previous model of Arista switches that we were using, the 7150 line. Basically, TCAM is it's a type of memory used by some network devices for things like ACLs, and what it ultimately did was it limited what ACLs we could use. So we wanted to do IPv4 ingress and IPv4 egress and IPv6 ingress and IPv6 egress. And so ingress and egress being the ACL gets applied to traffic as it enters the switch, and egress being the ACL is applied to the traffic right before it leaves the switch. And where you'd want to do this is if you want to send traffic to different tools. For example, you want to send, DNS traffic to one tool and HTTP traffic to a different tool. And basically what it came down to was the TCAM is arranged in slices on that switch, and it reserves some slices at the beginning for, system purposes and capping. But to do a full length host specific IPv6 ACL, like a /128, required too many slices that were available in that first half, because there was also this limitation where you couldn't have an ACL cross the midpoint of your TCAM. And so we could only fit it on the second half, but at the same time, we couldn't have our ingress ACLs and our egress ACLs occupying the same space in the TCAM. So basically we could do /32 ACLs for IPv4 ingress and egress, and we could do a /128 of IPv6 ingress, but we couldn't do egress. So now I mentioned that's on the old 7150 line. We no longer use those. We use 7280s, which use virtual output queues instead of TCAM. But there are other limitations. Like I think the last time I checked, you just couldn't configure an IPv6 egress ACL on the 7280s, even if you wanted to. So fortunately, there's a workaround to that. If you need to do an egress ACL for some reason and you can't, what you can do instead is just apply it as an ingress ACL and use this little hacky workaround of installing a cable between two interfaces. And basically you would configure your tap group here. So it could go down and send to your tool here, like normal, or it can send over to that looped cable. And then you can apply the ACL as the traffic re-enters your switch here in a different group and send it to your tool. Now it does have some limitations. You're going to be capped at the link speed of these interfaces that you're looping that cable through. So if these are 10 gig interfaces and you're bringing in more than 10 gigabits per second of traffic, you're going to have to cut down on the traffic some other way before you send it out here, or you're just going to oversubscribe that interface. And then also it's a little expensive. You're burning 2 ports on your tap aggregation equipment for every ACL that you want to add, every egress ACL you want to add. But it does technically work, and it's something that we are using in a few places. So not so much a limitation, but a challenge that I ran into when I first started working with tap aggregation equipment was we're bringing in all these, hundreds of taps from all over our campus, and we didn't have a way to basically identify where a single connection was seen in our campus. Obviously you have IP addresses and MAC addresses, but we're running into situations like broadcast storms or routing loops, and it would be very useful to be able to say, okay, this specific the specific link is where that traffic was seen, and we didn't have a way to do that until I found out about these things called identity VLANs. And this is basically where you can apply a VLAN tag to each interface on your tap aggregation. So you can pass that VLAN tag all the way down to your tools, and then you can identify which interface it was on and then which link that interface is fed from. And this basically uses Q and Q for those familiar with it. So even if there's a production VLAN that you need to preserve for some reason, it's still there. Okay, so last few topics. I want to talk about how we address tapping email in the cloud. So in the olden days, we had an on-prem SMTP relay, and we did unencrypted SMTP, and it was super easy to just install a tap, and there you go. You would have all of your unencrypted SMTP traffic going to Zeek or whatever tool you wanted. But then, we need to modernize and move our email up to a cloud-based SMTP relay, and we need to start doing TLS for encryption between relays. And so both of those things would take away our visibility into email traffic. So the way we approached that was we enabled something on our cloud SMTP relay called dual delivery, which is basically, it says for every message in or out of your organization, send a copy of it to this other place. And in our case, that other place is a server that the cybersecurity group runs on-prem that has Nginx to terminate TLS and then give us an unencrypted SMTP stream that we could just send to a tool. But what we actually do is we loop it through a fiber. Basically, we just have a NIC with fiber plugged into it, and then that goes to a tap, and then it goes back to that server itself that's running SMTP sync in a jail that just dev nulls that traffic. But that lets us take the output of the tap and plug it right back into our existing tap aggregation infrastructure, basically as if nothing changed when we moved from an on-prem SMTP relay. I think we had to make a few whitelist changes for the IP addresses used, but otherwise I think our Zeek policies and our tool configuration all remain basically the same. And then, so this isn't really a tapping or tap aggregation topic, but starting to think about how we get visibility into the cloud. We've played around with something in AWS where basically we're attaching a mirror session to the virtual interface of an EC2 instance. And you can do this across VPCs. So if you have users or customers that are in one VPC and then you have your security group tools running in a different VPC, you should be able to mirror across them as long as you get the permissions and security group config set up correctly. But there are limitations to this. So I think there are throughput limitations and number of session limitations, and it might just, you might have to get the configuration management worked out ahead of time. If you have hundreds of EC2 instances or they're popping in and out of existence, you might have some automation you need to do there. We're not doing this widespread at the moment. We basically just use it for our malware sandboxing. So if we want to detonate malware in the cloud, we just go and spin up an EC2 instance, attach our mirror session to it, and we can go and generate Zeek logs and tune Zeek policy based on that traffic without having to run it on our production network where we're risking other things. Okay, last topic is tapping 400 gig Ethernet. So we don't have 400 gig TAP-AG online just yet. I think we just brought up our first 400 gig peering to ESNet in the last couple of months. But I think we are stepping it down to 100 gig and tapping at 100 gig until we get the 400 gig TAP-AG equipment and taps installed. So there are two models from Arista that we're planning to purchase or have already purchased and are waiting to arrive. The 7280 CR3 and 7280 DR3. So the CR3 has lots of 100 gig ports and a handful of 400 gig ports, and the DR3 just has a lot of 400 gig ports. We are planning to do lots of testing with those because we know when we went from 10 gig to 100 gig, there wasn't quite the same feature parity there, and it took a little while for it to catch up. And then Ryan Walker from University of Illinois pointed out that the taps may only be rated at 100 gigs. Even though they might work at 400 gigs, the manufacturers may say you have to use the 400G PLR4 optics, which basically break it out to 4 by 100 gig streams, and you'd have to put it through 4 100 gig taps and then recombine it after doing so. Our plan is that we're going to test both of those things, and who knows, maybe by the time we actually have all of our equipment, there will be 400 gig rated taps as well. As far as how that will change our tap aggregation infrastructure, we're planning to install the CR3 model switches kind of in the aggregation role, so we can land lots of 100 gig links on it and then use their 400 gig ports as our inter switch connections, basically to output to the output layer switches. The one exception being in our int DMZ and intranet TAP-AG infrastructure, because we will have so many links. Our plan, and we have some 400 gig links as well. Our plan is to use the dense 400 gig switch as kind of a central place to aggregate all the aggregation layer switches, and then just land our 400 gig Ethernet taps directly on that, rather than purchasing yet another 400 gig capable switch to connect to it. Okay, so I do have an appendix with a few more slides, things like hardware examples, looking at our Zeek cluster hardware configuration examples. For the sake of time, I probably won't go through those. But if anybody has questions or suggestions, I think we have some time for people to bring them up now, or of course, feel free to send me an email. This is my email address, or you can send it to security@lbl.gov, and be more than happy to hop on a Zoom with you, or just exchange emails.
Right, great. Thanks, Michael. If anyone has any questions, you can either unmute yourself or you can type it in the chat there. We'll see how it goes. So. Do you have any other, I'll start with any other lessons learned you picked up so far when you go between different size? Have you been surprised by the ingested data or anything else you're seeing off that, or any things like that as you switch from interface speeds or what you're collecting?
Not really data wise. I think I do have a fun story about Cynet, actually.
Okay.
The first time that I was having to work with real 100 gig optics, we had a link that would come up just fine at 100 gig, and you could do performance tests over it at 10 gig, I think maybe even 20 gig, just fine, like no packet loss. But when you tried to do 100 gig over it, it would it just fell down. And I think what we ended up having to do was clean and reseat all the optics in the path, and then it worked fine. Even though it had good light levels, I think the theory there was that forward error correction couldn't keep up, and it was just generating so many errors that it was just dropping packets. And so that's kind of here's why getting the fiber right can be so important when you're talking about these higher link speeds.
Great, sounds good. We have a couple coming in from chat. The first one is, how do you manage all the configs and the TAP-AG switches? They have Ansible question mark.
Completely manually at the moment. So
Okay.
would like to do Ansible at some point. We use Puppet for all of our Zeek nodes. Maybe if we could use Puppet for our Arista switches, that would be less learning curve on our part, I think.
Yeah, okay. Another question from chat. Maybe you can't say, but are there also stateful firewalls in any of these paths? I think the diagram just shows some of the switches and routers. So do you have any firewalls in mind?
Yeah, so we don't do a big central firewall. We have a handful of distributed firewalls basically in front of specific systems or groups. So HR, finance, business systems have stateful firewalls. We used to specifically install taps both outside of and inside of those firewalls. We effectively now still do, but they are actually a single tap, because what we're doing is VLANs, kind of like a router on a stick or firewall on a stick. And so the internal VLAN does still cross a firewall, but it's the same tap that the external VLAN does as well.
Okay. The next question, the recall Mozilla article about 100 gig Zeek tunings for a single node a year or two ago. What is the current quote real world limitation on a single node capturing?
Yeah. So I don't know the current status on that.
Okay.
I can probably get you in contact with Ashish, who's our local Zeek expert.
Okay.
We aren't even doing 40 gig on a single node. The closest we have is our experimental, what we call cluster in a box, that I think has something like 8-10 gig interfaces on it. I don't remember how many sockets or cores that it's actually running. I think it's running something like 80 Zeek worker processes. But we're not doing 40 gig or 100 gig NIC in that box. It's just a whole bunch of 10 gig NICs. But yeah, I can pose that question to Ashish and see if he knows what the current state is.
Okay. I should have scrolled up and read the rest of the question. So the follow on to that is perhaps more directly, is anyone doing single 100 gig Zeek boxes with no drop packets, or is clustering almost always necessary? So you kind of answered some of that. So
yeah, I don't know of anybody doing single Zeek nodes that way. I think our perspective on it has always been that it's easier to do clustering than trying to get the tuning right for those high speed links or high speed NICs.
So the next question. Yeah, we'll share the slides after this, if that's okay. I think you said unclassified on there. So, but
Yep.
is that all right?
Yep.
Okay. Next question, what is the maximum number of taps and tool interfaces that you have on a 17280 TAP-AG?
Off the top of my head, I believe we have a 48 port 10 gig that has something like 40 tap interfaces plugged into it right now.
Okay.
And then it has, two tool interfaces to go feed down to the output layer. I was actually talking to Ken before the start of this. We had purchased a 72 port 2U 40 gig, 100 gig Arista for part of our tap ag infrastructure, and then never actually ended up using all those ports until the end of maintenance contract arrived. And so rather than renewing maintenance on it, we ended up turning it over to our networking group and replacing it with a 36 port 40 gig 100 gig Arista, just because it was cheaper to buy the 36 port than renew maintenance on it.
Okay. One question, can you discuss any interesting findings from the Zeek nodes? Anything that helped with troubleshooting or unexpected security finds?
Yeah, so the first example that comes to mind is not a security topic, but a network troubleshooting topic. So we use Cloudflare as our reverse web proxy. And basically, when somebody wants to spin up a web server at the laboratory, we have a requirement that they need to use Cloudflare to front end that web server. But we have a genomics group that is doing like very large data transfers. I think they are like 80% of our data transfer, or like our throughput through Cloudflare. And they were wanting to do something like 900 gigabyte file downloads or something like that from their web server. And their connections would get cut off at, I think, like 990 gigabytes. And there wasn't any very obvious way to see that just in the Cloudflare logs or in the Cloudflare interface. So we actually ended up going to Zeek and looking at the byte counters for their data transfers and seeing like, oh yeah, every time it gets near this threshold, it's getting terminated. And so we could take that to Cloudflare support, and then they take it to engineering and they're like, oh yeah, there's this undocumented, unpublished limitation on the amount of data that you can transfer in a single connection.
That's always nice, Jeez. Yeah, and then she just shared a couple links here and said you have to run a Zeek cluster, either cluster in a box or a multi-node cluster, but this is all scalable. So any other questions from anyone? Either put them in the chat or you can unmute. Okay, last call. Dan just mentioned they deployed some AP5Ks, correlate off with 100 gig capable Zeek box as well. So they just shared the link in the chat there. So okay, I think that's all. So thank you again, Michael. I appreciate it. And like I said, we'll get this recording get set up, and we'll get the slides out there as well. And I want to thank everyone for joining, and we'll send out an update for the next talk. All right. Thanks again.
Thank you.
All right. Bye.